go from Coulomb's law to introduce the flux density and then to introduce Gauss's law. So to be able to have enough tools to solve problems, right? So far in the previous lecture on Friday, you saw that we had Coulomb's law, which in fact the one you see here, all right, is right here. And with this one, where now in this particular case, you see, I also have to remind you that there are two ways of writing Coulomb's law. One is by explicitly incorporating the unit vector, all right, along the direction of the force. And usually Coulomb's law is like, if you look at this one here, to write Coulomb's law practically, you have to have two charges. You cannot write Coulomb's law without having two charges. So in this case, there is a charge capital Q and there is a lower observer charge lower Q. And the force in between them is written in this form here, where A sub r is the unit vector along the direction that connects the two charges. And also, since the two charges are positive, it forces the, say the Q charge is gonna be forced away from the other charge, all right? So that's the direction of the force on charge Q. And this force is given by that. Okay. Now, in these ones, assuming that we are in free space, also to remind you, we have epsilon naught and we use that is in farads per meter. From Coulomb's law last time, we then introduced the concept of the field, all right? And how then, instead of talking about the force F, that the little q is going to feel, the observer, the little q is gonna feel because of the capital Q, then you're talking about the electric field that is exerted at the point where the observer is because of the charge, capital Q, which is now the source, all right? So when we talk about forces, you need two charges. When you talk about fields, you need one charge that produces it, and you call this charge the source. It's the source that produces the electric field. All right. We are going to introduce this, the electric flux density here, and then we are going to also bring it back, remember. So for now, we introduce as a new vector, vector D, and we call that the electric flux density. And it is measured in farads, volts per meter squared. And why is that? In fact, this is because of here, all right? So here for my presentation, I will go through my notes, but when you read it, you will see all of this. So why we introduce D as the electric flux density? Why do we call it flux density? Because the electric field is measured in volts per meter. The electric impact, to be accurate, we should call it the electric field intensity, but we drop intensity because it's too long, all right? And we call it electric field, but it's in volts per meter. Now D, which is epsilon naught times E, if you plug in there the electric field expression, which we got from Coulomb's law, then what you see is at the end you have, in fact, if you go up here, epsilon naught is in farads per meter and E is in volts per meter. So if you go here, you see farads per meter, volts per meter. Farads times volts gives what? Coulombs. Because you remember how we define the capacitance? As charge per divided by voltage, Q over V. equals C. Capacitance is in farads. Q over V is Q over V volts. So farads times volts gives coulombs. Therefore, D is measured in the form of coulombs per meter squared. It's therefore charge has the units of a charge per area. That's why we call it density. All right. Okay. Now, therefore, we have so far introduced Coulomb's law, the electric field from Coulomb's law, and then the electric flux density. Okay. Now, we are going to introduce a theorem, okay, and we are going to do it in a way that is going to help us find a simpler way of calculating electric fields. Now, why do I say that? You remember when we tried to calculate the electric field from two charges? Last time we took one charge, we expressed in the Cartesian coordinate system, we took the other charge, we expressed its position, we found the vector that connected the two charges, all right? And then we found the E that was on the other charge, and then we found the electric field from one charge and the electric field from the other charge, and then we tried to superimpose them in the Cartesian coordinates. All this is good and fine. It's a process that is not difficult conceptually, but mathematically you have a lot of things to do. And that is a good process if you have point charges. All of the charges we have seen so far, like these ones, these two, this one, and where are this one, the other one? And these two are charges that have a particular value in coulombs, all right? And then they are sitting at one point in space, even if when I show them, I do a little circle around them, they only occupy one point in space. That's what we call them point charges. As opposed to point charges, which exist, in theory, and just because we want to make things easier. And this one is even a point charge, all right? What you see here is also a point charge, this one. All right. In reality, charges are not in points. Charges distribute over a surface on metals, and charges in other materials distribute over a volume. So let me give you an example. Now I hold this one without feeling anything, all right? And why is that? Because all of the equipment here is grounded. If the equipment was not grounded, all right, and usually it's grounded through the power outlet, brings a ground. If the equipment was not grounded and it was sitting on a wooden table, say, and I was holding it and I was sitting on the ground, barefooted, without shoes that have plastic, all right, then I would feel a lot of charge. I would be shocked, when I would charge this, because positive charge accumulates and accumulates everywhere, all right, on every surface, and then stays there because there is nowhere to go. I mean, in fact, what is positive charge? The lack of electrons. So there have been positions without an electron in there. So there are holes, we call them holes, because the electrons gone. So that's a positive charge. And then if you try to hold it, why I feel, what happens is that all of the free electrons I have in my body will try to go here and bring balance, all right? The charges are attracted. So you feel that that's the kind of this sense you get when you are shocked. If, however, I were to use plastic shoes, I don't touch the ground, so I would not feel anything. But why is it that I feel this? Because it's not just my body electrons, it's the ground is like a sea of electrons. Let's assume that my body has whatever electrons it has. If there was a lot of charge here, I would not be able to produce enough, all right, to bring a total if there is a lot of charge here. However, a lot of charges come from, and that's why a lot of people die, from a heart attack because the charges come from the ground, go through your body, all right? And then until they come here to neutralize what it is. And if there are a lot of charges that go through and your heart needs heartbeats, all right, heartbeats creates, it needs a signal that goes like a beat, or whatever, how many beats per second, then it stops. That's why you die, all right, from a heart attack, because your heart stops. You're not burned or something. You burn because, you know, people, there is horrible images sometimes from like it's not like you burn. I mean, maybe because the heat is very high, all right, if you have a lot of charge, but in reality, you die from heart attack, first of all. That's it. So we ground them. So charges go everywhere. They take the shape of whatever holds them. The shape of a metal, usually they're gonna go at the most, you know, sharp points, the shape of a dielectric, and so forth. So in reality, the charges, if we have charges that then have occupied the volume, we would like to be able to learn how to find the total field. Well, there is a way of doing it if this volume has a spherical symmetry, as we call it. But to be able to do that, we need to incorporate in our thinking a theorem. It's not new to us, that is called the Divergence Theorem. And as a matter of fact, it's a mathematical theorem. So I will go here to my notes to be able to explain it. So what you see, the typed is above, the notes are like more explanatory below. All right, so first of all, there are two things that we are going to introduce here, the Divergence Theorem and also Gauss's law, which is here. And you're gonna see it also later. I mean, there is some kind of connectivity between all of these. There is no one way of introducing one after the other. It's like a circle, all right? So that's why sometimes you will see people that introduce these topics in a different way. So for example, the circle is, let me do it here so you can see it better. I will do it right here to see why it is introduced in a different way from what the book is introduced. There's things. So in electromagnetics, there are the following concepts and expressions and laws rather. So it's Coulomb's law, Coulomb's, for forces. It's from Coulomb's law, you can go to the electric field. All right. And then from the electric field, you go to electric flux density. And from there, you go to Gauss's law. And from there, you can go back to Coulomb's law. Now, this is one way of introducing the field from Coulomb's law, like this, counterclockwise, as we call it. Clockwise, rather. Okay. There is another way of introducing the same concepts. You can start from Coulomb's law, or you can start from Gauss's law, whatever. All right, let me do this. I start from here. You go to Gauss's law. You can go to the electric flux density. You can go to the electric field. And then you can go back and find Coulomb's law. So sometimes you start it here. Sometimes you can start here. Sometimes you can start here. It's like this circular, you know, they all belong to the same circle, and then you can introduce the different concepts in a different way. That's why you're going to see the different ways of introducing the concept. But what we are following here is to go from Coulomb's law, we did the blue one here, all right, to electric field, electric flux density, now to Gauss's law, and somewhere here in all of this is happening, has a backdrop. All right, the backdrop to all of this, there are two mathematical concepts at the backdrop of all of this introduction. One is the divergence, the concept of that, the operator. And the other is the divergence, so this is divergence on a vector, say A. And the other is the divergence theorem. All right, we saw divergence, now we have to introduce the divergence theorem. And as I said, it's the backdrop to all of this. Okay, so we have now introduced divergence, and now we are going to introduce the new concept, the new law, which is called the Gauss's law. And Gauss's law, and you can prove it from anything, all right? All of these, one proves the other. It's a very circular kind of thing. Gauss's law says the following, and I want you to remember it separately. I don't want you to remember it as the result of a mathematical. You know, the law is a law, you need to remember it the way the law is, even if it's derivable. It's not like one of these fundamental, like, for example, when people came with Coulomb's law in the beginning, they did not even know how to prove it. This particular one came later, all right, historically, it's derivable. So the divergence of the electric flux density that is due to a point charge is equal to this point charge at the location of this charge, all right? So obviously what that says is the following. If I have a point charge here, at that point, this is true. This relationship is true. Because the divergence of a vector is an operator, all right? So an operator operating on a function, in this particular case is the electric flux density, it shows in fact the electric flux density, which is like a scalar times, a constant times the electric field. Is nothing else, but it's another way of representing the electric field. But we call it density because the units change. But if the field goes like from this, if the field is like a solenoid and it goes from this end of the room to the other end of the room, the electric flux density is going to go exactly the same way, along exactly the same lines. It's just the value that it's going to have is going to be different, but it's going to look like exactly the electric field. Okay, so that says that the divergence of D, so the del dot D, del dot is an operator. When this operator applies on D, then it creates a function, all right? It's an operator on a function, it creates a function. So D is a function of X, Y, and Z, or D is a function of rho, theta, Z, or rho, phi, Z, or D is a function of R, theta, and phi, or R, phi, and theta, however you want to have it. All right, so in every cylindrical, in every coordinate system, Cartesian, cylindrical, or spherical, D is a function of that space. Okay, an operator applying on a function gives a function. So ideally, if I were to erase that for a moment, and I say, okay, what is this? I will say it's a function. If somebody were to tell me what would this give, I would say this is a function, f, of space. If this is X, Y, and Z space, it's going to be X, Y, and Z. If it's a spherical space, it's going to be R, theta, and phi. All right. What Gauss has told us is that this function is nothing else but the charge that is distributed in that space. All right, so this is charge distributed in this space. In that space. Okay, when you have a point charge, how does this charge distribute? Is Q at one point, the center of the spherical is 0 everywhere else. All right, if you have a point charge only that produces the field, that means that this F function is nothing else. So I will write here F is practically Q when R equals 0 and theta and phi, whatever values they have. If R equals 0, then you collapse to the center of the coordinate system, all right? And F of R, theta, and phi is 0 everywhere else for every R which is different than 0. So that is important to remember because this is how we define a point charge. The charge is at one point and is 0 anywhere else, all right? So that's why you have that, and let me move this a little further down. You have that divergence of D. When you see that, it means this is at where Q is distributed is Q, and for our case, for point charge, is 0 everywhere else. So at point charge. And it's 0 everywhere else. We will see later that if the charge distributes, then wherever you have charge, the divergence of D is equal to that charge at that point. All right, and then it's going to be 0 at every other point that does not have charge. So that's how this is the general. Okay, so now we have a point charge. And what we would like to do is to apply the divergence theorem, which in fact, it's here. What does the divergence theorem say? The divergence theorem is right exactly here. Just put this one, oops, this one. All right, it says that if I have a volume V within a space where I have an electric field and therefore an electric flux density, all right, let's assume that I have this electric field that I told you, electric flux density, any volume in here, the volume integrand of that electric flux density is equal to the closed surface integral of this electric flux density. And then here we are describing it below. All right, so what you're going to see here is the original point charge, and then I choose the point charge is where the red is here. In the upper one, it is where the green, let me do the red, both of them. So this one, and also it's here. And what I do, I take the first case where it's just in free space and I sit at one point, and then I define a sphere around it. Why do I define this sphere around it? Because this particular charge distribution is spherically symmetric. So keep that in mind. That approach we are using here with the with the divergence theorem is only good enough to use and simplifies your calculations when your charge volume is spherically symmetric. A point is spherically symmetric, all right? If it is at the center of the spherical coordinate system. But it could be any other shape that is spherically symmetric. So for example, another sphere that is, whose center is at the center of the spherical coordinate system is a spherically symmetric shape, all right? Okay. So now I consider this volume V, and this volume V has a surface. Every volume is surrounded by surface. Every finite volume is surrounded by a closed surface. Do you agree with me? Okay. If it's a sphere, the volume is like the volume of a sphere, then the surface that surrounds it is the surface of the sphere, okay? Now, if the volume is scalar quantity, what is the surface that surrounds it? Is it a scalar quantity? A surface is never a scalar quantity. Every surface has a direction. Why is that? Because this surface here, this wall, and that wall, are they identical surfaces? No. One has a direction like that. There's nothing behind the wall, all right? So I'm only here. So the direction, this surface looks like this. So it has this direction. And that surface looks this way. It has an opposite direction. These two surfaces have the same magnitude, but they have different directions. So the surface is a vector. This surface is a vector. And as a matter of fact, is a cylindrical surface. And the vector of the surface always goes outwards. All right? So spherical. The sphere, the surface of the sphere has a vector, and the vector is this little n that you see here is in a unit vector, and it always goes outwards on this surface, away from the particular, in this particular case, away from the charge that has created the electric field. All right, so it's n. Now, the divergence is a differential operator. Do you know what differential operators mean? As opposed to being an integral operator, all right? So derivatives are differential operators. Integrals are not differential, they're integral operators, that's the fundamental, all right? A differential operator applies to a teeny surface, a teeny volume, a teeny line, just around the point where you make the calculations, all right? It does not extend beyond that. So for example, if you say that the derivative of the electric field at this point is this much, that implies it's only here that has this value, all right? So it only applies at one point, okay? Therefore, when we have the divergence of D, practically the value of this new functional, all right, of this function, we said the divergence of this is another function. So the value of this function applies to a point. Therefore, we take this divergence of D, which is also a scalar because you have the del, which is a scalar, inner product with another, the del, which is a vector, inner product with another vector. So the inner product gives you scalar. So the divergence of D here, it's a scalar function. You take therefore this, and then you plug this scalar function into a volume integral, which is also scalar, because volume is scalar. Volume does not have direction. The volume is a volume, it's what it is. There's no direction to it. Okay, so what the divergence theorem says is that the volume integral of this scalar del dot D is identical to the surface integral on the surface that completely surrounds the volume of the vector D dot the infinitesimal vector delta or ds. All right, the vector ds is an infinitesimal vector, and it represents a tiny area on the surface of this sphere. And as a matter of fact, this tiny area is here. All right. And we said because its surface is a vector, so this vector ds vector is equal to a value ds, which shows the area, times this vector n. Okay, so then you have here one scalar in a scalar integral, And here, a surface integral, which is a vector by itself, but now it applies, the vector for the surface has already been incorporated in ds, all right? So you have an inner product between d and ds, and you take then the area integral of that. An area does not have vector, but surface does have, an area is not a vector. But surface is a vector and has direction. And therefore, what happens now is the following. If you take the surface integral, look at this, the charge that produces the electric field, therefore the electric flux densities at the center. And the electric field relates to this charge and is only a function of r, where r is the distance from where I am from the charge. So if I am on the surface, all right, the distance for someone on the surface from the center is just r, which is the radius of the surface, of the sphere rather. Okay, therefore, we also know that d dot ds, it's, well, before we go there, we know that del dot d is q, all right? So all of this volume integral, it gives you q practically. And so from here, you can write it like this if you like. So what I did here, however, I did something different. You can do it in many ways, but in this particular case, I took this theorem for granted, and then I took, instead of the volume integral, I took the surface integral. And then I took the surface integral, I plugged in for d, which is here. And then I wrote ds vector like this, as we explained. And therefore, after that, I pull the vector n, inner product d, but I use for function for d what we had from Coulomb's law. This is from Coulomb's law. Okay. And then what happened using Coulomb's law is you find practically you move this, the delta dot AR is nothing else but 1, because D has the direction of AR. All right, so D, if you remember, let me write it here, where D, it's up there. I will write it again, where D equals, from Coulomb's law, 4 pi AR over R squared. All right. So if I take this D and I plug it here, if I take this one and I plug it here, practically I have the inner product between two ARs. AR dot AR, what does it give me? What does that give me? 1. You remember, a unit vector inner product with itself gives 1. Okay, so that gives me 1. And from here, I go to this expression. Now, then I move, since I am on the surface of the sphere, I move what is a constant out and what is a constant in this one. Why is this a constant? Because Q is what it is, it's a point charge. And R on this surface is equal at all points of the surface, because this is the surface of a sphere. So at all the points on this surface are away from the center of the sphere by the radius of the sphere, R. So that's constant on the surface. And therefore, what remains here is this integral. What is this? This is the integral of the surface on its entirety, the integral of the tiny surface on the whole surface, all right? This one is defining ds vector is an infinitesimally small section of the surface, all right? So if you integrate that infinitesimally small, the magnitude of this infinitesimally small area, the vector, if you integrate that over the whole sphere, what are you going to find? You have, the surface of the sphere. You have a sphere, you have its surface. If you integrate this infinitesimally small surface that we have defined, this, if you integrate it around all the surface of the sphere, what are you going to get? You're going to get the surface of the sphere, the area of the surface of the sphere. Do you agree? How much is the area of the surface of the sphere? Here. The area of the surface of the sphere, to be accurate, that's area. Okay, to be accurate in how we use words, even if a lot of times we drop things. It's 4 pi r magnitude squared. So then, if I plug this result here, go back and plug it here, what do I get? I get this result, which is Gauss's law. See, that is Gauss's law. So now, having proven those things, I'm going to go back to the circle that I showed you here. And what I wanted to say is, now, if you start with one law, you can prove the other. If you start with Coulomb's law, here, and you can find electric field. After you introduce electric flux density, you can prove Gauss's law using the divergence theorem. Or you can start a Gauss's law, and then you can go the other way and you can prove Coulomb's law. All right. Now, when we have to find, so practically we have two major laws we are using to find the total fields from various sources. We can use either one of the two. They're equivalent, obviously, because from one you can go to the other and the reverse. Which one you're going to use depends on what kind of source you have. When the source is symmetric, either cylindrically symmetric, as you will see, for an infinite, assuming that it's infinite along the other direction. If it's infinite along the z direction, but has cylindrical symmetry, like a long wire, right? Or if it is spherically symmetric, we always use Gauss's law, and we start from there to find the field, that you will see in a number of examples that we will do today, and we'll do also Wednesday, and we'll do more examples on Friday. From Gauss's law, you can find the electric field with fewer steps. However, if it happens that your sources do not have a particular symmetry, then you always start with Coulomb's law. And then either you superimpose the sources if they are distributed anywhere, like charge is distributed in position, like point charge is distributed, I will use the superimposition. Or in fact, if there is a whole distribution, like an arbitrary distribution of a charge, assuming that the charge is along this cylinder and has this tap here, and then you want to find the field from a charge like this, then you have to go to Coulomb's law, because this one is, but it is cylindrically symmetric, but it's finite in the length as opposed to below. If, for example, you wanted to find the charge on something like this, if there is charges, then you will have to go to Coulomb's law, because you cannot see a particular symmetry here, right? So that's why we have these tools right now. We have two important tools to use. Okay, so having said that, this is explanation, electric flux. These are all things we are going to start solving examples. Okay. So this is one example where we are going to find the electric field out of Gauss's law. All right, and make sure that it's exactly what we were supposed to have from Coulomb's law, okay? Coulomb's law says that if you have a charge Q like that, at any point at a distance r, you can find your electric field. But now, we just solved this problem before, so we're not gonna do it again. But since it's a point charge and the same on the sphere, then now you can use Gauss's law. In Gauss's law, you have to define a volume and a surface that is consistent and similar in symmetricity, in being symmetric with the source. All right, so if the source is a point, then your volume can be a sphere. If a source is an infinite long wire, your volume can be the volume of a cylinder. Okay, so you can apply those. So you select the volume, and then you follow the steps that I follow. You take the divergence, Gauss's law, you're applying the divergence theorem, and then you get the expression for the electric field. So in this particular case, you find that, so I just want to show you, it's very similar to what we did before. You take the Gauss's law, and then you take the divergence theorem, like you do here. All right, you did exactly the same as we did before for the surface. You find that. And then from there, knowing that d sub r is nothing else but epsilon E sub r, as here, then you find the expression for E, epsilon I said, for E, the electric field. So in fact, that's another way of going back to Coulomb's law. But you see how then, without knowing even Coulomb's law, let's assume that I only knew the divergence theorem and Gauss's law, then I can derive it. I can derive what we found with Coulomb's law. Now we're going to go to something more complex, obviously. All right, that was the introduction of the concept. But before we go to something more complex, we are going to introduce some more concepts, some new types of entities. So let me remind you that we have seen the point charge. Point charge here, which is Q and has the units of Coulomb. Now we are going to talk about a line charge. So if the charge is not at a point but extends along a line, we call it a line charge. Remember that the line is infinitesimally thin. All right, so when you say line charge, it does not mean a strip. It does not mean a round with finite dimensions. It means a very thin, long line. Surface charge is the charge that applies on the surface only, all right? And the total charge, it does not matter how it distributes itself. The total charge always has the units of Coulomb. And finally, the volume charge. The total charge, even if it's volume, is going to have the units of coulombs. However, when we go to distributed charges, instead of talking about the total charge, we talk about the charge densities. Why is that? Because a charge may distribute along a line, but it may distribute unevenly. All right, so it might be very high at the ends, might be very small at the center, for example. To be able to characterize and talk about that uneven distribution of the charge, you have to introduce a new concept, a new entity, which we call the line charge density. If the charge applies uniformly on the line, then the line charge density is going to be obviously the total charge divided by L, but only for the uniform distribution, all right? So here I will write it. Remember, uniform distribution. If the distribution is not uniform, of course, that does not apply. You will have somehow to find the derivatives of the charge to see how the density applies. But in any case, let's assume uniform for now. Surface charge density, if you have a charge applying on the surface in a uniform way, then we can define the surface charge density as the total charge divided by the area of the surface. And if you have a volume and the charge distributes uniformly in this volume, and these are mostly all the problems we are going to do in this class. All the problems we are going to do in this class, we will assume uniform distributions. All right, because otherwise, of course, in life, all of the distributions are not uniform, but we don't have the tools to calculate the electric fields. However, for DC cases or low frequencies, analog low frequencies, then we can still assume uniform in some cases, all right? So this is all very, very practical, I would say. So also pay attention. Line charge density is in coulombs per meter, measure units. Surface charge density is in coulomb per meter squared, and volume is in coulomb per meter cube, all right? So I don't have max, but you will see I came exactly to the same place where I was in the morning section. What we are gonna do next, the problem we are gonna solve on Wednesday, and then we'll solve more problems after that, because practically we're done with the theory. Now we have to put it to practice, okay? So the easiest next problem is going to be a charge which is equally distributed within a sphere. And then the question is, how much is the field inside the sphere? Because let's assume that the charge is in free space, but is all concentrated, all right? Equally distributed within a volume now. So the question is, how much is the electric field inside that? And how it changes as I move, if I am an observer, and I start at the center of the sphere, the charge, the spherical charge, and I start moving away from it, the question, and then I move eventually outside of this sphere, and then I keep moving away, the question is how the electric field that I feel is gonna change, all right? And we're gonna talk about that next time. And then we'll do some applications too. I will show you applications where this is important, all right? Any questions so far? So I'm gonna activate also your new exercise for Wednesday. And the new exercise, for a second. Okay, it's an interesting one. It shows you in this case, two different cases where there are 2 point charges. In one case, they're both identical there. The other cases, they're along the diagonal and they have opposite signs. And it says the 2 point charges at square vertices, 2 small charged bodies are placed at 2 vertices of a square in free space. The electric force between the charges is stronger for case A or case B or C. The forces are equal in magnitude for the 2 cases. So it's talking about not direction, but the magnitude rather, okay? Be careful, it's not the direction, the magnitude. All right, thank you.
Sorry?